Good morning. Okay, we are working on DC circuits, and we'll continue with that. We're actually going to finish up DC circuits probably next class. So our exam is scheduled for a week from Friday. That means we're going to be covering a lot of new material between Wednesday and our exam. So if you have strong feelings about whether you want to move the exam up so you don't have a lot of new material in between, we could do the exam on Monday, or we could leave it where it is and we'll have a lot of new material between now and the exam, but I won't test you on the new material, only on DC circuits. So we will continue with DC circuits. We are on Kirchhoff's rules. We were setting up a problem where we needed Kirchhoff's rules to finish it. So let's take a look at that. Just copy this, we'll move it over. So we came up with our junction rules. One of the first things you want to do when you get a circuit like this, so oftentimes I just try to reduce it down as much as I can with series and parallel first and get it to that point where I can't do anything anymore with series and parallel rules. And so this is one of those cases. We've got it to the point here where we can't do anything else with series and parallel. Well, how do we solve that? We need Kirchhoff's rules. So it looks like there are two junctions in this circuit, A and B, but really they're symmetric, I guess, if you want to call it. They both give you the exact same equation. Whatever current flows in at B flows out at A, or vice versa. So when we set up our junction rule, we saw that we immediately got the same equation. Where's our junction rule? There they are. Immediately got the same equation. So we could ignore one of them. There was no new information there. But that's one equation we need. I1 plus I2 plus I3 is 0. That's one of our equations. Then we went up and set up a loop rule, and we did this loop right here. We did this loop right here, the loop 1, the left side. And when you look at this circuit, it looks like there are 3 loops there. Let me draw them out for you. Loop 1 is the one I've indicated here with blue. Loop 2, I'll use green on this side, could be this half, right? And then loop 3 could be all the way around the outside. So if you use these 3 loops to be your 3 equations to solve for your 3 unknowns, I1, I2, and I3, and you do not use a junction rule, what's going to happen at the end is you're going to get 1 is equal to 1. Everything's going to cancel out because one of these equations contains no new information that the other 2 don't already have. What you see that once you've done loops 1 and loop 3, we've covered every element in this circuit. And loop 2 doesn't give us any new information. It doesn't relate anything that isn't already related. So we have to have the junction rule here. And we cannot use 3 loops. We can pick 2 of them. I like to always start at the same place. So I would do maybe 1 and 3. I start in this corner over here. I'll start in this corner and I'll go around the loop. I'll go around, find a loop until I come back to where I started. Then I'll start in the exact same corner, the exact same place, and I'll go around and try to include different elements. And I'll keep going around until I've included every single element in the circuit. That seems to be a good way because you want your loops, not only does each loop have to have a new element in it, a new device in the circuit, but it also has to have something that connects it to the other loop, or at least you'd have to add a loop that connects them. So I'll show you when we get to more complicated circuits, I'll show you what I mean by that. So we've already written the loop rule for 1, but I guess we could do it again. Let's write the loop rule for 1. We'll do all 3. We'll do all 3. But we know that we can only use 2 of these. So if we're starting in the lower left corner, we go up through the battery. Remember, it's like a hiking trail, and the direction you go around the loop changes your equation. So pick a starting point and hike around the loop in one direction until you're back where you started. I go in the low voltage side of a battery. I come out the high voltage side, so I've gone up by the voltage on that battery. I just rose by that amount of voltage. I'm going in the high voltage side and coming out the low voltage side of resistor R1. How do I know I'm going in the high voltage side and coming out the low voltage side? Because I defined it that way when I said the current was going in that direction. When you go with the current, you're going to a lower voltage. So I'm dropping by I1, R1. And I keep marching around my loop until I get to junction A, that point A, and then I go down that middle branch, and I'm going in the low side of R2, and I'm coming out the high side of R2. So I'm rising. I'm going up by the voltage on a resistor, and that's IR. Now I'm going into battery 2. I'm going in the high side and coming out the low, so I'm dropping by V2. Now I'm at junction B, and I go back to my starting point, and I have to, when I add all those up, I have to get to 0 because I'm back where I started. Okay, I'll give you a minute to do loop 2. We're going to start at point B, go up the middle branch, and around until you get back to point B again. You're going to follow my path around. So follow the green line. You're going to start at point B, go up, and then loop around to the right, come down through R3 and back to point B again. So starting at point B, we're going to go up the middle branch. We're going to follow my green path around clockwise. We're going to go clockwise around the right half of the loop here, the circuit. So up through the battery 2, we're going in the low side, coming out the high side. We are rising by V2. Then we get to resistor R2. We're going in the high side, coming out the low voltage side. So we are dropping by the voltage on that resistor. What's the voltage on a resistor? IR, that's a negative sign. Now we're at point A. We walk across the top and we go down through R3. We're going opposite the current. We're going in the low side and out the high side. So we're rising. And then we go back to point B and we don't hit any more devices, any more elements in our circuit. So we add those up and we have to get 0. We're back to where we started. All right, one more. We'll go around the loop 3, around the perimeter, the outside of the whole thing, around the perimeter. The battery is producing the current in the circuit, and there's current going into and out of the battery, right? You've been doing that in your DC circuit labs. You've tested, remember when we had series circuits and parallel circuits, you tested the current into the battery versus the current into all the resistors. When they're in series, it's all the same. And the current into the battery versus the parallel circuit, and they added up all the currents and the resistors added up to what was going through the battery. So there's current going through the battery. Y plus I3R3, because we're going clockwise. We're going clockwise around. See my arrow here? I'm taking this green path, and I'm going clockwise in this direction, right? Clockwise. And so that's why when you guess, you just guess. The first step is to just guess the direction of the current. Doesn't matter if you're right or wrong, just guess. I said right here, I said I3 is going in that direction. As soon as I said that, that fixed the potential difference across R3, as the bottom had to have been a higher potential than the top. So when you walk around the green circles, what I call loop 2, when I walk around loop 2 and I get to the top of this resistor R3, I'm at the low voltage end of that resistor. So let's just draw a resistor here. If we say the current is going this way, if we say the current is going that way through the resistor, then the left side of that resistor has to be at higher potential than the right side. This side has to be higher potential than this side. I'll call this A and this B. the voltage at A has to be greater than the voltage at B. That's what the little plus and minus sign mean. The voltage at side A has to be greater than the voltage at side B. Why? Because positive charges, remember, current is the flow of positive charges. Positive charges are flowing to the right through this resistor. Why would they go to the right? Because the electric field points in that direction. It's pushing them in that direction. Why would a positive charge go to the right? Because there's an electric field here, right? That's the only reason a positive charge would go in that direction. Well, electric field always points toward lower potential. Positive charges flow from high potential to low potential. So if the current is really going from A to B through that resistor, the only way that could be happening is if A is at a higher potential than B. If B was at a higher potential, the current would be going the other way. So we just guess the direction of the current, and then that fixes the signs through all of our equations are based on that. And then I'll show you what happens if we guess wrong. All right, so let's quickly get this last one. We've got a plus V1. We're starting at the lower left corner. We're going around clockwise around the circuit. We go in the low end of V1, come out the high end. Now we're going with the current. So we are dropping by I1, R1. Now we cross over point A, but we don't go down the middle branch. We keep going around the outside until we get to R3. We're going in the low side, coming out the high side. So we are rising. And now we don't encounter anything until we get back to where we started. So that's it. So those are our three equations. We'll pick two. It doesn't matter which two. And we'll use a junction rule. Okay, so let's put some numbers in so you know what to do. That's an omega. Okay, so if we plug in these numbers, so these solving, what are we doing? We're solving simultaneous equations, right? We've got three equations, three unknowns. One way to do it is just power through it, doing a lot of algebra until you've figured it all out, right? That's one way to do it. The other way to do it, you all have those fancy computers that can solve matrices. Learn how to set it up as a matrix, let it solve it for you. For three equations, three unknowns, maybe it's not a big deal, but if I make this circuit a little more complicated, all of a sudden we have 5 equations and 5 unknowns. Cranking through all the algebra is pretty time consuming. If you learn how to use the feature on your calculator to solve these simultaneous equations, it's a lot quicker. Yeah, linear algebra. Okay, so when you crank through the equations, this is what you get. For the first, let's say you solve for I3 first. And you get negative 171 amps. So what does that minus sign mean? It means you picked the wrong direction. I3 really does not go up through the resistor R3. It's really going down. That's what that means. We guessed the wrong direction. But all of our equations are based on that. So you need to use negative 171 for I3 as you go through and solve for other things you're looking for. We're still looking for I1 and I2. So I just solved and got negative 171. Then for I2, I get negative 0.283. Now, if I want to get I would use my junction rule. I1 plus I2 plus I3 is 0. But I need to retain the negative sign for I2 and I3 because all of my equations are based on the directions I picked, and I got those directions wrong. So as I go back, I keep those negative signs until I've solved for everything. Once I've solved for everything, I get rid of the negative signs and I say the current's really going the opposite direction. So I would get I1 plus negative 0.283 plus negative 171 is 0. I1 is 171.283. So what does this tell me? So let me just highlight this. Keep the negative sign until you have solved for everything. That's everything. How did I get I1? I did a lot of algebra. Yeah, you got to crank through and do the algebra or use your calculator. Now your calculator will give you all the answers at one time. You don't have to worry about it. But if you're cranking through by hand, doing the algebra, solving the simultaneous equations, eliminating one variable, then the other one, doing lots of algebra, then you're going to get them one at a time like this. So the actual does it have to be a graphing calculator? I'm not sure. Does anyone know? This is my 10 volt. This is my 12 volt. The actual current flow is like this. I got the direction right on I1. Remember I said all three went up, and I knew that at least one had to be wrong. That's why I wanted to show you what happened if you got a negative sign. So we know that I1 is correct. We got a positive number for that. And both I2 and I3 were wrong. I got negative numbers. So instead of up, they both go in this direction. So this circuit is used for recharging a battery. This is a circuit that's similar to a recharging a battery. It's flowing the current backwards through battery 2 here, through our 10-volt battery, and that is reversing the chemical reaction in that battery and recharging the battery. Okay, ready for a more interesting one? Okay, think about that one for a second. We're looking for, so if we're given, again, given the resistance values and the voltage values, we're trying to find the current in each branch of this circuit. What's the first thing you're going to do? If you take the circuits class, if you take engineering 37, learn how to do circuits, there's a slightly different technique they use, but it's basically the exact same thing. They combine the junction rule and the loop rule into one step. And it's, I don't know, I don't think it's any easier or harder. It's just slightly different. But you get the exact same equation, and it's basically the exact same thing. So we'll do it this way. Have you defined all your current directions? Most of the time, the battery pushes the current in the direction of the voltage of the battery, right? So we would expect we would expect the current to be coming up in each of these due to those batteries, but we just saw in our previous example that's not always the case. But if you're trying to guess, that's a good guess. And if those three are all coming up, then what has to be happening through 4 here, resistor 4, then that has to be going that way, right? So we could just go with that if we wanted to. And remember that this is one branch over here, I4. If I4 is coming to the right, where is it going? It's also coming down here, and it's also going over here. That's one branch. There are no forks in the road. There are no junctions for it to split off. Once we get past this junction right here, once we get past that junction, whatever current we have has to stay the same until we get to another junction. That. And the same with I1. This over here has to be I1, and this over here is also I1, right? There are no junctions anywhere in there. If that helps you a little bit, go ahead and draw it like that. Okay, that's the first step. What's step 2? Junction rule, right? Sum of the current into a junction equals the sum of the current out. There are 4 junctions here. I'll pick, call this A, and this B, and this C, and that one D. Let's go ahead and write out those 4 junction rules. I guess I probably need to define 2 more currents here, don't I? I'm going to call this current I5, and this current, I'll just put it this way, I6. So let's do A and B first. The current, there's no place for it to go. So we said that the current through this resistor is I1. So if the current through that resistor is I1, then just trace it. Then it has to be the same everywhere until you get to the next junction, which is right here. Then, so it's all the same there. And going backwards, the same thing is true. It can't change until you get to a junction. So at junction A, what do we have coming into junction A? I1 and I2. What do we have coming out? I5. So junction A tells us I1 plus I2 is equal to I5. And junction B tells us I6 is coming in and 1 plus 2 are coming out. I6 is 1 plus 2. So A tells us that 1 plus 2 is 5, and B tells us that 1 plus 2 is 6. So what did we just learn?
I5 equal to I6.
I5 is equal to I6. Does that make sense? Let's look at our circuit here. If we put a big black box around this, we can't see anything in there. And we know that I6 is running in this side. Well, if no current is getting into my black box from some other source, and no current is leaving to some other place, then what must be coming out at the top? The same amount of current, right? So whatever goes in at the bottom has to come out at the top. Think about like water flow. If this is a hose and water is running in the bottom, and there's no water leaving our box, and there's no water coming into the box from some other place, then the same amount of water has to be coming out the top. So it makes sense that I5 and I6 are equal and their directions are opposite. So I guessed the directions, I got them right because there's no minus sign here. I got the directions right. And the magnitudes are the same. Well, what does that mean about junction A and junction B? It means I got the same equation. I got no new information from junction B after doing junction A. So that doesn't help me. So this really is just one junction rule. The only thing it told me was that I5 and I6 were the same. So let's go do C and D. And what do you think is going to happen when we do C and D? We're going to get the same equation, right? But it's going to be different from the one we got with A and B, hopefully. Let me write in here. I'll write this. A. So C tells us that 3 plus 5 is equal to 4. And D tells us, I'm just going to call this one I5 since I know that they're the same. Tells us that 4 is equal to 3 plus 5. So junctions C and D give the same equation. So on first glance, when you look at the circuit, it looks like there are 4 junctions, but really each one has a counterpart which gives us the exact same equation. So how many junctions are we getting out of this? 2. We're getting 2 junction rules out of this. Remember, how many equations do we need? 5. We need 5 equations to solve for 5 unknowns. We're looking for 5 unknowns. 1, 2, 3, 4, and I guess I5, right? I should write here I5. We want all 5 of those. So here are our two equations, and we need three more. So now we look at loop rules, right? And it's nice to mark the high voltage side of each device. It just makes it a little easier to get your signs right later on. Let's see, what am I going to use? Green. So this would be positive, negative, positive, negative, positive, negative. Batteries, doesn't matter what direction the current is flowing, the long line is always higher potential than the short line. Resistors, it depends on what direction you chose as your current. So if the current is flowing up, the bottom is at higher potential than the top. And if it's going down, the top is at higher potential than the bottom. So there's a number of different loops here. You see that? I can see, let's see, 1, 2, 3, 4, 5, 6. I can count 6 different loops that I can draw. I can pick any of the small ones, right? 1, 2, 3. That's 3 right there. I can do a double on either side, and then I can go around the whole thing, the perimeter of the whole thing. I can count 6 different loops I can draw. But we need 3 loops. Let me show you why you need 3. You might think you can get away with 2. If you draw a loop on the left side, let's draw a loop on the left side. I'll use blue, and I'll draw this. Oops, what did I just do? Hate that. Come on. Okay, we're back. If we draw the loop on the left side here, I'll use blue. Start in the lower left corner. I'm going to go around my loop in this direction. Call that loop number 1. Doesn't like circuits, I guess. So my loop is including V1, V2, R1, and R2. Now I draw a loop over here. I say, I need to get every device included in my loops, right? So I'm going to draw a loop over here. I'm going to use green. I'm going to do this loop. I got V3, R3, and R4. So I've covered everything. I've got every resistor included in one of my loops. I've got every battery. You might think you're done. You might think that any new loop doesn't give you new information. But you'd be wrong because the 2 loops don't share anything in common. So there's nothing that links them together. Not only do your loops have to include every single element in your circuit, So these two loops include every single element. The loops have to connect with one another, at least with one of the elements. So I would need a third loop. I could pick the loop in the center, and that would connect them together. I could pick the perimeter, right? I could, anything here would really, any third loop would connect these two together. One thing I like to do that usually works is I always start in the same place. So if I start in the lower left corner and I do loop 1, then I start in the lower left corner and I do loop 2, but I go out and I make sure I include at least one new device element. And I still have one more hanging out there, R4. Then I start in the same place and I make sure I include everything, something new. Usually that technique makes sure you have the right number of loops in the end. But the idea is you want to include every device in your circuit has to be included in at least one of the loops, and the loops have to overlap. There has to be something that connects them together. So we'll do these 3 loops that I just drew, 1, 2, and 3. Let's do those. Loop 1 is the blue one. It just goes around that left side, the smallest loop. We go in the low side of battery V1, come out the high side, so we rise by V1. We go in the high side of R1 and out the low, so we drop by the voltage on R1. We rise by V1, we drop by the voltage on R1, and what's the voltage on a resistor? IR. Then we're going into R2. We come around the loop, get to junction A. We say we're going to go down through that middle branch. We get to R2. We're going in the low side and coming out the high side of R2. So we are rising. And then we get to the battery and we're going in the high side and coming out the low side. And then we're back to where we started. Yes, you could do the 3 small loops. You could do this. You could do loop 1, loop 2, and loop 3. Yeah, that would work. That would be fine because these 2 are connected here. These 2 are connected here. Every single device element is included, so that would work. Where are we? Number 2. Number 2, the first 2 are the same, right? And then we come down through the middle branch. So we've got an R3 and a V3 there. So we've got a minus, we've got a plus I3, R3, and a minus V3. And then we're back to where we started. And the third loop starts out the exact same way. And then we get to the 4th resistor over there. We're going with the current this time. And then we're back to where we started. 3 loops. Two junctions. Those are the 5 equations you need to solve this. We'll take a 10-minute break. See you in 10 minutes. Okay. We'll see if you get the hang of picking the direction of the current. So for this circuit, given So if you're given that equation, can you go back and figure out what directions I chose as my currents in these branches? I like to start with one of the potentials of the batteries because that tells me what direction I'm going through that branch. I have a positive V1, so I must be going in my loop. I'll use blue for my. I must be going in this direction because I just rose by the voltage on V1. I can't be going the opposite direction. Now it tells me minus I1 R1. So I'm going with the direction of the current. I'm going in the high side, coming out the low side, in the high, out the low. So the current is going this way. And then I get to R2 and it says it's minus I2 R2. So I must be going, I'm coming this way through. So the in the high, out the low, I'm going with the current. And then I go in the high side of the battery, come out the low side, and I'm back to where I started. Okay, now let's do the other one. Let's do one more. They're not related. Start with the potential on the battery, negative V3. So we're dropping through battery 3. We must be going in this direction. Then we get to I3, and we're adding the potential there. So we must be going opposite the current. We must be going in the low side, coming out the high side. So the current must be going that way. We keep going until we get to the other side. We are rising again, so we're going in the low side, coming out the high. So the current is opposite our direction. And then we get to that battery and we are dropping. We're going in the high side, coming out the low side. So that all makes sense. That all works. That's how I grade these, right? I pick something in your equation and I start walking through the circuit and I look to make sure everything makes sense in your equation. There are no inconsistencies. Oftentimes on the exam, what I do is I just say, give me the equations you need to solve for these 5 currents, or to solve for whatever, these 5 things, the battery and those 2 currents or something like that. I'll just say, give me the equations needed to solve for these, because otherwise there's a lot of algebra, or you're just plugging it into your calculator to get the answer. So once the equations are written, the physics is done at that point. I assume you know how to do algebra, or you could figure out how to use your calculator to get the numbers. Usually I just stop you there and say, give me the equations I need. And as you saw in lab, the loop rule works for other things also, not just resistors and batteries, but capacitors, anything that we know the potential difference across. Like a capacitor, we know what the potential difference is on a capacitor, right? It's Q over C. So if you're doing a loop rule and there's a capacitor there, you could have a Q over C for the delta V across the capacitor. That works also. Okay, let's do a few of these. Okay, so if this is ground right here, what's the potential that over here? What are we calling that? Point B, point something, X. So this tells me that this is all zero. That's what that symbol means, right? Ground. That defines zero potential. And if this is 12, if you start at 0, you go through a 12-volt battery, you have to be at 12 volts when you come out the other side. And we've got two equal resistors here, so you kind of knew right off the bat it had to be halfway in between. But you can just count, you can just figure out the delta V's across each device. So if we have half an amp coming through here, and the resistance is 12, is that what I said? 12, then V is equal to IR. So a half times 12 is 6 volts. I have to drop by 6 volts going through that resistor. If I came in at 12 volts, then I have to be 6 volts less than that on the other side. So this has to be 6 volts. Okay. Yeah, the voltage drops across each resistor. You come in at 12 volts to the first resistor, you know you have to drop by 6, so you must be at 6 volts when you come out. And the same is true for the second resistor. You come in at 6 volts, you know you have to drop by 6, so you have to be 0 when you come out the other side. Then there's nothing else, right? No more potential drops. You're at the lowest potential at that point. All right, if we have 2 amps coming out of that battery, it comes to that first junction, it splits. Part goes through one resistor, part goes through the other. Because the resistance is the same for both and the voltage is the same, the current ends up being the same. So 1 amp goes this way, 1 amp goes that way, and they meet up again at the bottom and become 2 amps going back to the battery. Okay. Let's just speed through a couple of more of these. You just use V equals IR for each one. You know delta V is 12 volts. You know the R's, so calculate I for each one. If they were different, that's what you would do. Okay, as you walk around that circuit, just think about what happens in each device. So you go in the low end of the battery at 0 volts, you come out, you have to be 12 volts higher. The battery maintains a 12 volt potential difference. Now you're at 12 volts. You hit resistor 1. You know that you have to drop by I times R going through that resistor. So 1/3 times 12 is 4 volts. You have to drop by 4 volts. If you came in at 12 volts and you drop by 4, you're going to come out at 8 volts. It's like elevations on a hiking trail. Now you stay at 8 volts until you get to the second resistor. You go in at 8 volts, you know you have to drop by 4 volts. I times R is 4 volts for this resistor. So you have to come out at 4, and then you go into the third resistor at 4, and you have to drop by 4 through that resistor. 1/3 times 12 is equal to 4. So you come out at 0, and that all works. It's because you're back to where you started. If you don't get back to where you started, there's a problem. All right, let's move on. So we've got 6-volt battery. We've got a switch here, and we're going to hook up a voltmeter across it, and 2 resistors, and an ammeter. So fill in the table, basically. It's only one switch. These are ideal. Okay, with that switch open, what happens? No current flow, that's correct. Because the voltage meter, the voltmeter, is an infinite resistance. So no current can come through here. No current can go through there. Right? There's no path for the current to flow. No current. We can start using our colored pens if we want. Let's call this 0 volts. What's the voltage drop across an ammeter, an ideal ammeter? Nothing, because there's no resistance. How about a resistor? What's the voltage drop across a resistor? V equals IR. If I is 0, what's the voltage drop? 0. So we're at the same potential at the top as we were at the bottom. All of this is 0 volts. Now, what happens when we go through the battery? We rise by 12 volts. So the leads on my voltmeter are connected to what? 12 and 0. So when that switch is open, the voltmeter reads, sorry, not 12. I was thinking about the last problem. The last problem, everything was 12. I changed it to 6 here, didn't I? 6 and 0. Now what happens when that switch is closed? What's the voltmeter going to read? You should know, 0. That's right. It's shorted out. We've just shorted the two leads together. They have to be at the same potential. So if we come out of the battery at 12 volts, we're still at 12 volts over here, right? Gosh, I keep saying 12. 6 volts, 6 volts. The battery is a 6-volt battery. And the bottom we're calling 0. There's no potential difference across an ammeter. So we have 6 volts across each one of those resistors, which means we're going to get a current through each one of 1.5, right? So we add those together, we get 3 amps flowing through this circuit. I just always define the low. I mean, you got to define something as something. The only thing we know for certain, unless we see one of these symbols, unless we see this, if we see a symbol like this in our circuit, that defines 0 potential at that point. If we don't see that in our circuit, then all we know are delta V's. So I just pick the bottom of my battery, the low. I think that's going to be my lowest potential. I just pick a point to 0, and then I start going through and marking everything after that. All we really know for sure are delta V's. Let's take a look at that. I set it up on our PhET simulation. Where's the one? Here it is. FET simulation. I've got our ammeter. I've got a 4 ohm resistor there and a 4 ohm resistor there and a 6 volt battery. The switch is open. We are getting 0 amps and 6 volts as expected. Oh, sorry. Got to share it with you, don't I? There we go. Okay, we've got a 6 volt battery, 4 ohm resistor, 4 ohm resistor. There's a switch with our voltmeter connected across it and our ammeter. All right. So with the switch open, 0 amps, 6 volts. With the switch closed, 0 volts, 3 amps. It's very easy. I set this up just a few minutes last night. Very easy to go back and double check things if you're ever unsure of an answer, you don't have an answer to a question in the book, you want to check it, use the FET simulation. All right, let's go back to here. Let's do our worksheet. All right, we've got identical light bulbs and batteries. The first circuit just has 1 light bulb. The second one has 2. The third one has 3. It's asking for the potential difference, right? Potential difference between N and M. Figure them all out in terms of the battery voltage. A is just the same as the voltage on the battery, right? It doesn't matter if this probe is hooked up here or here or here or here. Anywhere on this is the same potential. And the same with this one. This is all the same potential. So this is just reading the battery. How about the next one? Yeah, the potential drops across the light bulb equal to the potential across the battery. Right? If you come in if this is a 1.5 volt battery, then this whole side is 1.5 volts. You go through the light bulb, and where are you? You're at 0 volts. And this whole side is at 0 volts. And for battery B, here for situation B, if those two light bulbs are identical, then they both have the same resistance. We know they both have the same current because they're in series. So they both have to have the same delta V, which means half of the battery voltage is across one of the light bulbs and half is across the other one. And we're only measuring one of them. And for situation C, we have 3 identical light bulbs. Each one has to have the same potential difference. So each one has to have 1/3 of the total, 1/3 of the battery's delta V. So if we rank them, A is the greatest, followed by V, B, followed by C. How about this one? Again, if you get out your colored pens, you'll see these are just connected across the battery. Every one of these is connected across the battery. Number 3. We're measuring the potential across that resistor, right? That light bulb. So that depends on the current going through it. Which one has the biggest current flowing through it? Here we have the resistance of our light bulb in series with another resistor. Here we have the resistance of our light bulb in series with, we could replace these two. What could we replace that with? A single resistor that has what resistance? R over 2. And I could take these and replace those three with the single resistance, R over 3. So the greatest current is in situation C. I set up the circuit here. I've got my battery, my light bulb. I'm set up to measure the potential difference across this light bulb. And then I have three other light bulbs here, but they're all off right now. So this, I'm getting ready to do situation A. I'm going to close this switch. And this is A. I've got the two light bulbs. These are off, right? There's nothing else, just two light bulbs in series. My voltage is half of what's on this battery, 4.5 volts. It's a 9-volt battery. Now I'm going to close the next switch. And actually what's going to happen is more current is going to flow, which means I'm going to get a bigger delta V there. It went up to 6 volts. And it got a little brighter, if you noticed. And now I'm going to close this and let's see what happens. It should go up a little bit more. 6.75. Because as I add more resistors in parallel, the overall resistance here in this lower part of the circuit decreases, gets smaller. And so the current in the circuit, the current through the battery actually increases as I add these extra resistors in parallel. Okay, last one. Okay. All right, as I said at the beginning, we will probably finish DC circuits next class, but our exam is not till a week from Friday. So that means we're going to have a week's worth of classes on new material before the exam, or we could move the exam up to Monday. I'll think about that. We'll talk about it maybe next time. If you get your pens out, here's your low voltage end of your battery. So N is basically hooked up to the low end of the battery, and the high voltage is here. So in these two cases, A and B, M is hooked up to the top of the battery as far as voltage is concerned. And in case C, it's halfway in between. You're in between the two equivalent resistors. Okay. Okay, I'll see some of you in lab. Actually, I don't think we'll spend a lot of time in lab because it's pretty complete. The write-up, I think, is pretty complete. I made a video. We're measuring the magnetic field in a solenoid. So we'll meet today, and I'll go over it with you a little bit, but I don't think we'll spend a lot of time on it because it's the write-up and the video I made are fairly complete. But we'll talk about it a little bit. All right, we'll see you later.